Okay, in this video, I'm going to discuss about the coordinate systems. So, when it comes to coordinate systems, we have Cartesian coordinate system, and we have spherical polar coordinate system and cylindrical polar coordinate systems. So, why we need these coordinate systems? In order to describe a position of something, or in order to describe a motion of something, some object. So, we need these coordinate systems. So in this video, I'm going to talk about the Cartesian coordinates and spherical coordinates and the cylindrical coordinates. So I'm going to start with this Cartesian coordinate system. So okay, in this Cartesian coordinate system, we are going to describe a position in the with using the x, y, z coordinates. So we will have this x hat unit vector along the x direction, and y hat unit vector along y direction, and c hat unit vector along z direction. So we have a, if we have a position like P, so this position consists of x, y, z coordinates. So that means that when we take the direction, it is along this x hat direction. We have x hat direction, we have x coordinate. So like this, if we draw this, the coordinate will be x, and if we take a look at the y coordinate, so it is in the y hat direction. So these x hat and y hat are perpendicular to each other. So that means we have this y coordinate. So that means the length to this vector, length to this position is going to be x and y. So now when it comes to the Cartesian coordinate system, we have another unit vector, that is the c hat unit vector. So it is in the z direction. So we have to use that coordinate, we have to use that unit vector as well. So if we draw c hat unit vector which is perpendicular to both x hat and y hat unit vectors, then we have another coordinate of position P, that is with a length of c. Okay, now if we say that this OP vector is let's say that OP vector is equals to S. So I'm going to represent my vector as S. So this vector can be written in terms of x hat plus y hat and c hat. So if I'm going to write the infinitesimal displacement vector, so this is the displacement vector actually. So if I'm going to write the infinitesimal displacement vector using the Cartesian coordinate systems, we have dx x hat, dy y hat plus dz z hat. So these are actually talked in the previous videos. So right now I'm going to introduce a new term, that is the infinitesimal volume element. So infinitesimal volume element can be defined as d tau. So this is the infinitesimal volume vector, volume element, infinitesimal volume element. So this can be written in terms of dx, dy, dz. So these are the coordinates actually, these are the variables actually. So if the volume is changing, so that means that we have to find dx, dy, dz. So these are the multiplication of dx and dy and dz is going to be my infinitesimal volume element. Because actually when it comes to the Cartesian coordinate system, it actually forms a box, forms a it's just like a box, just like a cubic. So when you're going to find the if you're going to find the volume of that cube or something like a shape of box, so you will have to find the height and the height and the length and the width of that box. So this is just like that. And previously I have talked about the gradient of a scalar. So gradient, when it comes to the gradient, we defined as this as del operator with t. So this t is a scalar. So from the Cartesian coordinate, I have mentioned that the if we take the gradient of something, the equation will be changed to different coordinate systems. So that means we have this equation for this coordinate system. That means w over w x hat plus w over w y hat plus w over w c hat. So this is just for the Cartesian coordinate system. We define this gradient for the Cartesian coordinate system, but when it comes to the spherical polar coordinates and the cylindrical polar coordinates, it's going to be a different one. So now these things are just seen in the previous video. I'm not going to talk about it further. So we have divergence of a vector. This is going to be a scalar actually. So we have wx over wx plus wvy over y and plus wvc over wc. So this is just the divergence. So we define this divergence for the Cartesian coordinate system, because that's why we have xyz here. Now if we have the curl, so that means del operator cross product with the v vector. So that means we can put this into the matrix format xyz hat, and we have w over wx, w over wy, and w over wc, and we have vx, vy, vc here. So at the bottom of the determinant. So if we calculate the determinant, we can get the expression for the curl v. So this is just from the Cartesian coordinate system. If it's going to be cylindrical polar coordinates or spherical polar coordinates, these will be changed. And another thing that we mention is that the Laplacian. So the Laplacian denoted as this actually if we have scalar function t, so the Laplacian of t is going to be written as del squared t. So this del squared t means that we have the del operator squared. So this is going to be a scalar. So we wrote that, so w squared t over wx squared plus w squared t wy squared plus w squared t over w c squared. So this is just the Laplacian by using the Cartesian coordinate system. So if we are going to use the spherical polar coordinates or the Cartesian, if you are going to use the spherical polar coordinates or the cylindrical polar coordinates, this equation will be changed in terms of the coordinates that we use. So right now I'm going to move to the second coordinate system, that is going to be my spherical polar coordinates. So from the name of this coordinate system, you can get an idea about this coordinate system, because we are considering a sphere here. In the previous, we have used Cartesian coordinate system. That means we are considering just like a box. So now I'm going to use the spherical polar coordinates to describe the position of P, the point P. So the point P has coordinates of r, theta, and psi in the spherical coordinate system. So I'm going to write r, theta, and psi. Okay, now I'm going to place this r, theta and psi in this coordinate system. So what I'm going to do here is that I'm going to have this OP here. So the length of this OP vector is going to be my r. So there is a unit vector along this r direction that is called r hat. So and this r hat is parallel to this r vector, and now we have theta over here, and theta is the angle between c axis and the vector that we are considering. So this is called the polar angle. Actually, this is called the polar angle, and we have a psi here. So psi is the angle between the vector and the x axis. So this is how we form. So if we draw actually a sphere, if we draw a sphere with a radius r, it is going to be look like this. So this is just the this is just like an element, infinitesimal element of the of a sphere. So right now I'm going to say that this is my a vector. So let's say that this is my a vector. So the a vector can be written in terms of r hat and theta hat and psi hat. So let's say we have a vector. So this a vector can be written in terms of r hat and theta hat and psi hat directions. So now I have used the unit vector of r hat, and now we have the psi. So how we find the psi hat unit vector? So that means that the psi is changing in this direction. So that means this has a radius of this kind of radius. So we need to find that radius. Actually, so when we see the when we see something, when we see an angle is changing, so that means we have to have this psi hat along this direction. This is perpendicular to this radius. So now we have going to place this psi hat along here. So this psi hat and the r hat are perpendicular to each other. Now we have theta here. So theta is changing towards clockwise direction. So that means we have to have that here. So this is the theta hat. So these r hat and psi hat and theta hat are perpendicular to each other. So the angle between r hat and theta hat would be 90 degrees, and the theta hat and psi hat angle will be 90 degrees. And if you consider any of the unit vectors, if you consider the angle between two of these vectors, it's going to be 90 degrees. So now I'm going to write the a vector. So a vector can be written in terms of r hat and theta hat and psi hat directions. So I'm going to write the I'm going to write the vector component along r hat direction, that is going to be a r, and a theta defined as the vector component along the theta hat direction. So this is this a psi is the vector component along a psi hat direction. So this is how we can define a vector using the spherical coordinates. Okay, I'm going to write the infinitesimal displacement in r hat direction. So the infinitesimal displacement along r hat direction. So when it comes to the infinitesimal displacement along r hat direction, we have it's the r changing of r is going to be dr, because infinitesimal amount of change in the r hat direction is going to be r dr. So it's going to be defined as dlr, and dlr is going to be equals to dr. And if we take a look at infinitesimal displacement along theta hat direction, so it's going to be changed with the radius as well. So because it's going to be just like a circumference, so we have that r, so we have it is changing with the r theta. So that means if the theta is changing infinitesimally, so that means d theta is going to be the infinitesimal amount of change. So that's going to be dl theta is going to be r times d theta. So right now, finally for the I'm going to write the infinitesimal displacement along psi hat direction. So the infinitesimal displacement along psi hat direction is going to be this radius times d theta. So now I have to find this radius actually. So this radius is going to be r times sine theta. So this is actually the horizontal component. This is just like a horizontal component of this vector. So now we have r sine theta times d psi. R sine theta d psi. So these are my infinitesimal displacements along r hat direction and theta hat direction and psi hat direction. So we can now finally we can write total infinitesimal displacement along total infinitesimal displacement of this vector. So it is can be written as dl. So dl going to be written as dlr r hat dl theta hat plus dl psi hat. So now we have found that the dlr and dl theta and dl psi, so we can substitute them. So when we have substitute r hat, and we have r d theta hat, and we have r sine theta d psi hat. So this is my infinitesimal displacement vector. So this can be written in terms of r hat and theta hat and psi hat directions. Okay, now I'm going to find the infinitesimal volume element. So infinitesimal volume element is going to be my infinitesimal displacement along r hat direction, infinitesimal displacement along theta hat direction, the multiplication of these infinitesimal displacement along r hat direction, theta hat direction and psi hat direction. So if we have the displacement, if you have the volume element as d tau, so the infinitesimal volume element is going to be dr times rd theta times r sine theta d psi. So this is going to be my infinitesimal volume element. So if we simplify it further, it's going to be r squared sine theta dr d theta and d psi. So this is my volume element. So we need this, we need them actually when we do some examples in EM theory and in quantum mechanics, so in somewhere, because we are using this spherical polar coordinate system. When we use spherical polar coordinate systems to calculate the volume integral, we need to have this volume element by using the spherical coordinates. So it's really important to know this. So right now I'm going to write the gradient, divergence and the curl with using the spherical coordinates. So previously we have seen that how to write the gradient in the using the Cartesian coordinate system. Likewise we can use spherical coordinates to write the gradient of something, some scalar. Let's say the scalar is t. So I'm going to write this grad t using the spherical coordinates. So I'm just going to write this one because I'm not going to prove this one. This is going to be just a little bit complex. So dabba t over dabba r hat direction. So now you know that since this gradient is a vector, del operator is a vector, so you know that when we have a Cartesian coordinate system, we used to have x hat, y hat and z hat unit vectors. But when it comes to spherical coordinates, your unit vectors are going to be r hat and theta hat and psi hat. So we will have theta hat and psi hat in the equation, in the expression. So but the components, vector components is going to be changed. So that's going to be 1 over r dabba t over dabba theta, and this is going to be 1 over r sine theta dabba t over dabba psi. So likewise we can write an expression for the divergence. This is just a actually this is just a general expression because I'm not going to prove this one. So when we have a divergence of a vector, it's going to be a scalar. So that means we have to have this r theta psi, and the vector components are vr and v theta and v psi, not vx and vy and vc, not the not that kind of vector components we get for the spherical coordinates, because we are using when we are using spherical coordinates, we have to have the r theta psi combination. So right now I'm going to write the divergence, write the expression for the divergence. So now we have 1 over r squared dabba over dabba r, and we have this r squared times vr. So now we have 1 over r sine theta, the partial differentiation of sine theta times v theta. So v theta is going to be the vector component of theta. So now we have dabba theta here. So look carefully, this is going to be r theta, and the other one is going to other partial differentiation is going to be with respect to psi. So now we have plus 1 over r squared sine theta dabba v psi over dabba psi. So this is going to be my divergence. So there is an expression for curl v as well, so I'm not going to write this one because you have to find this one, because I'm not going to write because this just like an exercise for you. So now when it comes to the Laplacian, we will have del squared t. So del squared t can be written as 1 over r squared dabba r squared dabba t over dabba r, and this is going to be partial differentiation with respect to r. So now we have 1 over r squared sine theta dabba sine theta dabba t over dabba theta this is going to be partial differentiation with respect to double theta, sorry, theta with respect to theta, and the final term will be 1 over r squared sine squared theta double squared t over double psi squared. So this is going to be my Laplacian by using the spherical coordinates. So you can see that the that how much changed, how much deviated from the equation that we got for the Cartesian coordinate systems. So these are totally different equations, because we have to use different coordinates for different places. So when we are using different coordinates for different places, the Laplacian and the gradient and the curl and the divergence is going the equations are going to be totally different ones. Okay, finally I'm going to find the relationship between the Cartesian coordinate system and the spherical coordinate system. So in order to do that, I'm going to find this x length. So x length is going to be my we have find that this is r sine theta, and we have a horizontal component here, r sine theta times the horizontal component of r sine theta is going to be r sine theta times cosine psi, and y can be written in terms of the, this can be considered as the vertical component of the r sine theta. So the r sine theta vertical component will be r sine theta times sine psi. So z coordinates is going to be my we have this r here, so the length of this vector is going to be r. So the length so the component along z axis is going to be r cosine theta. So this can be considered as the relationship between the spherical coordinates and the Cartesian coordinate system. So next and the final coordinates that we have to talk about is the cylindrical polar coordinate system. So right now I'm going to do that. So now we have the cylindrical polar coordinate system, because we know that we have to use different coordinates. Okay, by the look of this, by the name of this coordinate system, so you will have an hint, you will have an idea about what it's going to be look like. So this is going to be look like a cylinder. So actually when we have a cylinder, so the cylinder is in the circumference of this is in the circumference of this cylinder, and we have this cylinder over here. If we can draw a cylinder, so right now we have to find the radius of this cylinder. So it is going to be we can say that so this is the cross section area. So the cross section area, and so the cross section area is going to be like this. So I'm going to draw the radius of this cylinder. So now this is the radius. We can say that this is rho. So now from the cylindrical point of view, so now the cylindrical point of view, so the radius is going to be changed, and the c is going to be changed, and the angle, so because this position is going to be changed along this direction, so it is going to be changed, so this azimuthal angle will be changed. So this can be considered as psi. So theta is not going to be changed, because this when we are considering a cylinder, so this polar angle is not going to be changed at all. Now it is the time to mark the unit vectors. So this unit vector is going to be, because the rho is changing, the radius of this cylinder is going to be changed, so we have to use this rho hat unit vector along the rho direction. So now we have seen that the psi is changing because the p position is going to be moving towards this direction around the cylinder. Actually this point P, if we consider object, this object can move around this cylinder, so that means this azimuthal angle is going to be changed. So the azimuthal angle is going to be changed means that the it's going to be, there's going to be another perpendicular vector to this rho hat, that is going to be psi hat. This is the unit vector. So these both these rho hat and psi hat are going to be perpendicular to each other. And now we can mark the rho hat and psi hat in this point. So now we have this rho hat and psi hat. So now I can I have told you that the c axis can be changed, because when we use a cylinder, the height can be changed. So that means that we have to have this unit vector as well. So this unit vector is going to be c hat. So because c hat is going to be perpendicular to both of these, psi hat and rho hat. So that means the angle between c hat and psi hat is going to be 90 degrees, and the angle between c hat and psi hat is going to be 90 degrees. So this P point has the coordinates of rho, psi and c. So this is used in the cylindrical polar coordinates. So now if we can say that if we have any vector like A, like previously we did, so this A can be written in terms of rho hat and psi hat and c hat. So this means the vector component of rho hat is going to be A rho, let's say that. So this A rho times rho hat plus A psi, the vector component along psi hat direction, and this is going to be psi hat, and AC c hat. So this is an any vector. So this is a general expression for the any vector in the cylindrical polar coordinates. So now we are going to write the infinitesimal displacement vectors. So infinitesimal displacement vector is how much will it will be changed in the rho hat direction, the psi hat direction, and the c hat direction. So dl rho is going to be my infinitesimal displacement vector along rho hat direction. So it is going to be d rho, because this rho can be changed infinitesimally d rho time. So now d rho hat. So now the infinitesimal displacement vector along psi hat direction is going to be my dl psi. So dl psi can be written as, so this angle will be changed a little bit. That means for an example, let's say that it is changing d psi, little angle, a little angle is changed like d psi. So now when it is going to be changed for a little bit, that means that it is changed with the radius as well. So that means it is changing with the radius. So that means rho d theta, it's just like a circumference. So rho d psi hat. So this is the infinitesimal displacement along psi hat direction. So that means we have to find the dLz component. dLz component is going to be, so these are vectors actually. So dLz is going to be my displacement along z. So any height would be changed, so that means z component will be changed. So if this object moves upward direction, that means the z axis only will be changed. So that means we have to have c times c hat. If it is infinitesimal, that means we have to have that dc. So these are my infinitesimal displacement vectors along rho hat and chi hat, and this is chi hat and c hat directions. So I'm going to write the infinitesimal displacement vector. So that is just like a total infinitesimal displacement. So now we have dl rho, dl chi, and dlc. Now I can write d rho hat and rho d chi hat, rho d chi and chi hat, and we can write dc c hat. So this is going to be my infinitesimal displacement for the vector that we are considering. Okay, now I can find the infinitesimal volume element. It's going to be d rho d chi and dc. This is my infinitesimal volume element. So it can be written as rho d chi and dc. Okay, now we are going to find the relationship between the Cartesian coordinate system and the cylindrical coordinate system. So we have this x coordinate here. So x coordinate is going to be equals to rho cosine chi, and y coordinate is going to be the vertical component of this rho. So the vertical component of this rho is going to be rho chi sine chi, and the c is going to be just c. So this is the relationship between the cylindrical polar coordinates and the Cartesian coordinate system. So now I'm going to write the gradient divergent curl and the Laplacian to the cylindrical coordinates. Okay, now we have an expression for the grad t. So that is equals w t over w rho hat and plus w 1 over rho times w t over w chi hat plus w t over w c hat. So now we have the divergence of v vector field. So that is equals to 1 over rho partial differentiation of rho v rho with respect to rho plus 1 over rho partial differentiation of v chi, the vector component of chi with respect to chi. So plus the vector component of partial differentiation of vector component along z direction with respect to z direction. So this is going to be a scalar. So now we have the curl for v vector using the cylindrical coordinates. It's going to be a complex one, so I'm not going to read this one actually, because these are not going to be if you are facing an exam, these are given actually, so you don't need to worry about these things, because it's really hard to it's really hard to prove this one as well. So because since this gives you a complex complex expression, so you will have to have a very good mathematical background to prove these ones. So now we have the Laplacian with the help of the cylindrical polar coordinates, and now we have del square t. T is a scalar function, so we have 1 over rho the partial differentiation of t with respect to rho, and the partial differentiation with respect to rho. So now we have 1 over rho squared w squared t over w chi squared plus w squared t over w c squared. So these are the Laplacian and the curl and the gradient and the divergence for the cylindrical coordinates. So now you can have an idea about how much it is changed from this Cartesian coordinate system. Actually, there are complex expressions actually compared to the Cartesian coordinate systems, but we have to use them in different occasions. So I hope you understand this very well. So we will meet in the next video.